This is Lecture 6, Part A. What we want to get into today is register transfer notation, fairly simple, and what it is a way to describe more large circuits, such as circuits like a computer, which is essentially a bunch of registers transferring data around. So a computer in general can be modeled as a bunch of modules passing data around. Register transfer notation is going to support that. Later we're going to get in some just example operations, and then we're going to describe experiment 3 and some examples also. So the issue here is that we are going to kind of abstract our design to a higher level, and right now we have like black box diagrams and schematics and modules and stuff like that, but that's not quite good enough. We want something makes our job a little bit easier. So we started out, we didn't really start at transistors, but the gates themselves, we started at gates, are made of transistors. We didn't spend too long with gates because we kind of moved it up to the module level, and now what we have is a computer passing data between a bunch of modules, and so we want a new description here, and that's going to be register transfer notation. So what's great about it is typically computers use register transfer notation to describe their operations, and we will be doing the same. One thing to notice here is that we are working with computer circuits. Computer circuits are generally speaking a bunch of registers transferring data around. Now the notion of registers transferring data around means that these registers they have clock signals. They're generally they're only active on a rising edge or a falling edge of a clock signal. So these circuits are synchronized to something, and that will be like a system clock signal. And we've used system clock signals practically with all our circuits. It's just some type of master device to synchronize the transfer of data around in a circuit. So we just generally call it a clock. Now, so another way to look at this is you have a circuit. It has a bunch of registers in it. Those registers are transferring data around, but we have specific registers that do specific things, and so we give that a name, and that's micro operations. So generally, a micro operation is an operation that changes a register value. So you're essentially it's just some vernacular for you. You're very used to this. For example, just for a simple register, generally speaking, we are able to control the loading of them and controlling the clearing of them. Generally speaking, synchronous. Counters, generally speaking, we also had control whether they incremented or decremented, or I guess held also. Shift registers, we could control whether they shifted left or shifted right. And we lately got into memory, and so memory, you can read memory or write memory. Typically speaking, the writes are synchronous. Oftentimes you see memory with asynchronous reads on them. And lastly here is the notion is that RTL, or register transfer notation, RTL stands for register transfer language, is a notation that describes the transfer of data in a circuit. And let's just look at it. So this is high level. This is like definition of register transfer notation. And so once again, I even use both of these. Sometimes it goes under RTN, sometimes it's under RTL. Register transfer language, register transfer notation. Essentially a shorthand way of indicating data transfers in a circuit, register transfers. And this is the official definition right here, which is hard to read and understand. This is actually a better. So essentially, this describes some condition that controls whether this register transfer happens or not. Now, you can think of this as a register loading data. So it's getting a source from somewhere, loads it somewhere else. under these conditions, and the notion of a register, that condition would be a load enable or just a load signal. So let's look at some examples. So this is an example of the program counter, and there's actually an error in this, so I'm going to go ahead and scratch that out right here before we get into this thing. Okay, now this the program counter does two things. It loads the address of the next instruction in instruction memory, which is this right here, or it loads some other address, and that other address is associated with a jump. So if you this is the proper RTL for that statement. So if I'm loading the next instruction in memory, I'm essentially loading the program counter with the program counter plus 4. That goes into the program counter. That's going to be the new program counter value. And it's done under these conditions. There's 3 conditions there. I got to turn the reset off. I have to make the select signal such that it chooses the PC plus 4 source, and I have to turn the PC write on, which is essentially a load signal. So this is proper RTL for that. Now, the program counter also enables jumps, and this is an example of a jump here that I got it right now. So essentially when I'm doing a jump, I'm loading, this is an example of a JALR jump. I'm loading the program counter with the value right here. Okay, to make that happen, I'm not resetting it. I'm using a different select value than that one. So this is 0, 1, which selects this line to happen, and I'm going to write that register also. This is once again a load enable. Yes, so sorry about that mistake in here. You'd think I'd catch those in advance, but I don't. And moving on. So RTL, it's really, seriously, we use this extensively throughout the course. This is a screenshot from one of the cheat sheets, and you can see that these are the instructions. This is a short description, but pretty much every time you see an arrow pointing to the left there, it is a form of RTL. So that practically every instruction is described using RTL on this thing. So there's always a question of why are we using a left arrow on this thing? And the issue is, I think that was the first way it was done back when computers, particularly when microcontrollers were starting to be designed in, I think, the early 70s. So this is done by convention for no other reason, but everyone uses it, so get used to it. So additionally, we're going to look at these JAL, jump and link, and jump and link register instructions. This is the RTL associated with those things, and it's actually kind of important. We'll get into this later. So they actually, the JAL instruction, you actually have 2 things going on in this instruction. You're loading the address of PC plus 4, which is the address of the next instruction, not the current instruction. That is being loaded into a register specified by the instruction. Now that's the same thing. You can see the same thing going on with the jump and link register instruction. The issue is the PC is going to be loaded with a different value. Now the difference between these 2 instructions here is the new value that's going into the PC in a jump and link is based on just a number, which is a assigned extended immediate number, but the value that's going into a PC for the jump and link register instruction is based on an address. So you can see that there's a register as part of the address calculation for the jump and link register. And so you'll see this later. This is going to be used as a return from a subroutine. You don't need to know that now, but what I want you to take away from this is that Jump and link, it loads the PC. They're both unconditional jumps, unconditional branches or jumps. They both load the PC with a new value, but the value that it loads into the PC is different. Jump and link is based on a number. Jump and link register is based on a number, which is the number, and also a register. Clearly, you can see that clearly in the RTL. So lastly here, we're talking about RTL. It's kind of a shorthand way to describe circuits at a high level. Highly abstracted. Essentially, it describes the synchronous transfer of data between modules. And we, generally speaking, when you write RTL, the clock signal is never listed in RTL because it's understood to be there. So there's essentially all the register to register transitions or transfers are synchronous. So we never write a clock signal when we're using RTL.